Okay. The main goal of this presentation today is to introduce you to the concept of electronic system in high energy physics. I have broken down this presentation into 4 quadrants of sections where each are of 15 minutes each, and it will going to introduce 2 different concepts of high energy physics. The first one will going to be about introduction to high energy physics experiment and electronic challenges, understanding the difference between trigger and timing signal, discussion on signal aggregator, and the third section, the process of embedding those timing signals and information in data signal. And last but not the least, application of FPGA in high energy physics experiment. So what is the need for high energy physics? What do we mean by that? High energy physics basically explores what the world is made of and how it works at the smallest and the tiniest particle level. And it is always reaching out for new reaches of discoveries where the mankind has not reached before. And for example, if you look here, the Big Bang picture is here. This is the picture of the galaxy. This is the heavy atom, then black hole and gravity star. And if you go at the microscopic level, you could see that these are all neutrons, protons, quark gluon plasma, and neutrino, and all those stuffs are there. But what happened during the Big Bang, just few microsecond later, that all these were in the particle state. And from this particle state, all of these were slowly coagulated and come together to form the galaxy. So the main purpose of the high energy physics is to create the very energetic conditions that existed within a billionth of a second after the Big Bang, and allow scientists to study the fundamental ingredients of matter. That's the universe is made of. And these high energy physics are also popularly known as particle physics. So I just give you a brief introduction of the term high energy physics. Next, I'm going into how to create such a condition close to Big Bang within a laboratory. Now there is a state diagram. If you could remember your chemistry classes, there's a state diagram of water. Similarly, there is a state diagram of attaining this quark gluon plasma. And as you can look into this graph, there is a phases of nuclear matter. On the x-axis is the density, and y-axis is the temperature in mega electron volt. If you go in the high density area, like for example, the matter changes from neutron gas to neutron star and slowly to quark gluon plasma. We are actually interested in this part, the quark gluon plasma part, because this is actually the separated part of the particles. And y-axis is the high temperature. Now, as you can see, some of the reactors names are given here. This is VECC Kolkata. This is where the reactor that is at Kolkata is operational. It works in the nucleon zone. And this is the critical point. Here is the Large Hadron Collider about which I will going to talk. And this one is the FAIR experiment, and here is the CBM. I haven't typed it here. This is a new experiment coming up in Germany, is in this part. And so you can see using high temperature, we can also go look into this quark gluon plasma, the nuclear phase matter. Now, how we can attain such a high temperature? The quark gluon matter in the laboratory is formed by colliding heavy ions, either lead ions or proton-proton ions, colliding head-on. Like head-on means, as you can remember from the CRO concept in electronics, it is colliding at the head-on at the micrometer level, and even less than that, nanometer. And this collision has to happen at the ultra relativistic energy. And during this process, It compresses and heats the colliding nuclei in a way that the individual protons and the neutrons superimpose with each other. And this creates a high density of matter, and which allows for relatively large number of deconfined quarks and gluons exist for a very brief period of time. The QGP state then slowly revert back, that is this part, will slowly fall back into the cooling area. And so, as you can understand, we get this temporary matter for a very nanosecond level, sometimes even at picosecond level. So it's like a camera shutter, which will have to capture these particles and boom, it's gone. So that has to be the accuracy level of the electronics. Now, in the next slide, I will going to show you the video of Large Hadron Collider at CERN. So before I play the video, I just want to give you a very brief introduction to CERN. CERN is in Switzerland, Geneva. It was created in 1954 with 12 European countries as the founding member state, with a common goal for nuclear research. Today, CERN is the world's largest research laboratory with 22 member states and 4 associate members. India has been a special observer since 1991 and is actively involved in many scientific and technical cooperation with CERN. The collider, I'm not going into too much technical details, just to understand the terms such that you can follow the presentation. Just remember that the collider at the CERN is called Large Hadron Collider. And this collider actually collides 2 particles head on, as I was mentioning in the previous slide. And then we capture the particle, the temporary or transient particles, using a very sophisticated mechanism. So I'm not playing the video. I want to interrupt here. So this is the collider, what you can see from the top. This part is in France, part is in Geneva. It is going underground. It's a 27-kilometer long Large Hadron Collider. And the particles are pumped in here for energies. There is a superproton synchrotron, proton synchrotron, and then those particles are thrown in this big collider and is collided head on. So I'm not going to interrupt the video again, and just watch that part carefully.
Go is a state of mind.
This part of the video shows after the collision is done, how the data is traversed through the different computing architecture and the electronics architecture to different parts of the world. So I'm just replaying this part.
Go is a state of mind.
Okay, so that was just a small glimpse of the complex architecture that was the CERN. For this presentation, you need to remember the terms, that is the Large Hadron Collider, and the another term is the ALICE experiment. There are 4 major experiments at CERN: ALICE, LHCb, CMS, and the ATLAS. So I think
Sorry, I'm unable to perform that task.
And of these 4 experiments, I will just talk about I will highlight the ALICE experiment part. These 4 experiments are dedicated to look into different frontiers of the high energy physics. ALICE experiment looks just at the time microsecond after the Big Bang. So it creates those laboratory situation. I don't want to go deep into that. I want to keep the focus on the electronics side. So the next part, what I want to highlight is this one: the data volume expansion that is going around in the high energy physics. As you can see, in the event generated per link per second is in megabyte. Next, the data transmitted per channel is in gigabyte. Total data transmitted per second in CERN that is at ALICE run 3. Run 3 is actually the run that is supposed to be going on by now, but because of COVID-19 that is delayed. And this is in terabyte. Per experimental year is in 50 picobyte, greater than 50 picobyte. That's why it's called picobyte. And data generated over such large experiment like CERN, if all the experiments are integrated, it is of the order of exabyte. And just to give you the picture of the data currently that is there, that is the worldwide one-day broadcast information is in zettabyte. Digital universe of today is in yottabyte, and rest is. So you can see how exponentially we are going into the data volume expansion. So high energy physics is actually leading this curve and pushing the technologies ahead. In the next slide, I just want you to understand the types of signal broadly in high energy physics that are very critical. We can broadly group the high energy physics signal into 3 parts: timing, trigger, and clock distribution signal. And this is one of the signal which is commonly referred to as TTC signal. Second is the pre-physics signal or the post-process physics data packet. This is the second type of signal. And the third is the control, configuration response, and monitoring signal. As you can understand, in any control system, it's a normal thing to have that such kind of a dedicated signals. What I will going to cover today is this timing, trigger, and clock distribution signal. And this signal requires a very critical handling. Okay, so this, I just completed the section 1 of the 15 minutes time. So in this 15 minutes of this section, you learned what is meant by high energy physics, how the LHC data taking flow look. I know it was a very quick exposure, but still you will take time for digest the information. Next is the data volume in expansion. And the fourth, that is the high energy physics signal that that is the timing signal that requires critical handling. Now I am going into the section 2 of this talk. In the section 2, I want to cover the concept of time triggering. So what is meant by a particle event in the terms of particle physics? A particle event is a particle collision or interaction that is observed by some type of particle detector. Detectors are LIC, act as a sophisticated camera, which I have already mentioned in the first slide, to capture those subatomic events. Here, again, I'm just throwing you some physics jargon at you. If you can remember, it's good throughout the talk. It will be easier to follow me. So this diagram is called the Feynman diagram. And this is how the collisions are represented in the physics, nuclear physics. So you have got the gluon particles that's coming together, and then at the final end is the Higgs boson particle. This is the recent discovery in CERN, because of which the Higgs got Nobel Prize. And on the left side, I just want to show you that how complicated this detection was. You are just getting this peak, nothing more, no more information for the experimental physicists to understand. You are just getting an expected background noise. Then you have got some data, and over this just a peak. And from this peak, you have to identify that this event has occurred, that is Higgs and boson are produced at the level of picosecond. That is the accuracy of the camera we are talking about. And LSC is able to capture that. And what LSC has planned, that in future experiment, it will going for much more sophisticated camera, such that it can go at the femtosecond level of capturing it. We are going actually crossing the picosecond level of the new upgraded version of the LSC. So this, in this slide, I want you to understand the definition of particle event. I'm just repeating myself once again. A particle event is a particle collision or interaction that is observed by some type of particle detector. In this case, when you produce, such that example, when you collide proton-proton, it generates quark, that's an event. In this case, there are collision of two gluon-gluon, it produces Higgs boson. I'm not going into the intermediate particle like beauty, tau, these are, I don't want to go into this. So from this product to this product, this step is called event. And this need to be captured in the LSC using the range of sub-detectors. Now the next concept you need to understand is the triggering of the signal. Now, as you can understand, it might sound that when you are capturing at the level of picosecond, you have got too much of data if you are capturing for even for a 1 second. So you can understand that you are capturing at the scale of picosecond and you are just capturing for a 1 second, and you're analyzing for all the possible physics particles that are generated at that time slot. It will be in millions of times higher and very difficult to process. So that's why there is a concept called trigger. So it is not going to capture the data every time. Whenever two particles collide, there will be an electronic pulse or a signal which will going to tell, okay, now open the window, capture the data, and once the window is closed, drop the data, whatever is coming from the experiment. So there are different class of triggers, types of triggers. I just give you the simplest example. Broadly speaking, the trigger has two basic roles: differentiate between the signal and background noise. And the second one, set the maximum data volume. And yeah, I'm just taking you through this flowchart. So once an event has been identified, say for example, a Higgs particle is detected, it will generate a trigger. And this will ask the DAC system to record the process of the computing. And this is the fundamental of trigger. But there is a catch with the Higgs, which I will cover in the next slide. So I'll just mention here, take for example, you get a quark, which is easier to detect because it is in the range of nanosecond, not in the range of picosecond. So this trigger is workable. It opens the window, asks the data acquisition system to capture the data. There is a time constant, which I have marked here. and it pushes to the computing sector to compute and record the data. Now, this is a very broad concept of trigger signal. I'm just not going into the depth of it. Next, I am taking into the concept of trigger rate. As you can understand from the trigger signal, the next obvious question, at what rate should the trigger be asserted? Let's go into that. The process to determine the trigger rate is very simple actually. The expected event rate equal to cross-section times of the collision particle, that is when you collide two particles, lead or proton head-on, then there is a cross-section of that, and that is represented by this sigma in, and times the luminosity. Luminosity is the reactor term. Avoid that for the time being. Take it as a black box. So you can think of luminosity like kind of a brightness in electronics, where you can control the number of particles bombarding together. So think of it like that for this talk today. Okay. Then total non-diffractive PP, I'm taking the simple collision, that is proton-proton. A simple proton-proton cross-section has got 70 millibarn. Then the production rate of a particle, this is a beauty, is a particle of in particle physics. It has of 0.7 millibarn is 1 kilohertz. So using this very simple calculation, that is division of the diffractive, that is production rate, by the production rate of the beauty particle, we get the trigger that is required to acquire this beauty particle signal. So it's very easy to calculate, but the challenge comes when you go into the Higgs particle. So next part, I'm covering about what happens when you go into the Higgs particle. When we go for the production of Higgs particle, the whole cross section of is around 1 picobarn. Now, if you just for your calculation, I've given it 100 millibarn by 1 picobarn. It is in 10 to the power 11, which is actually the trigger rate is in gigahertz, and that is not achievable real time. And this challenge is solved by going for a triggerless architecture. But mind you that when we go for triggerless architecture, we are also opening the door for big data volume. And keeping in mind the pros and cons on the either side of the world, the future architecture will have both the triggered solution and the triggerless solution. So this is a very simplistic view of the trigger signal and triggerless data distribution. We got a central trigger processor which gets the information from front-end detectors like whether a particle collision has started or not, and also a signal from the Large Hadron Collider, the main clock distribution chain, that whether the collision has initiated and proceed for the capturing of data. That part is called the determined by the central trigger processor. Then the central trigger processor sends a global trigger to the on-detector electronics. So the detector electronics, which I haven't mentioned before, in Large Hadron Collider, there are 4 main detectors, as I have told: ALICE, LHCb, CMS, and ATLAS. The purpose of this detector is to look at the particle collision, and each detector is looking at different physics aspect. ALICE is looking at the just a few seconds after the Big Bang. LHCb is looking at dark matter, and then others are looking at, say, if there is a graviton particle, and those type of stuff. Some are even looking at some interesting stuff like in the string theory, multiple universe, those type of things. And so the detector, there are different types of detector depending upon the particles that are there, and those are all put together near the collision area. And on detector electronics, this global trigger is sent. Now what this global trigger says, it actually says, it actually sends a window. When it receives a window or a pulse signal, it tells the detector electronics, okay, now open the data capturing window and take data and release the data. And from there, it goes into the data aggregation. Yes, I was hearing some feedback. Any questions or anything? Okay, then I'm continuing. Just let me know if there is some glitch in the audio. This on-detector electronics now then sends the data to the data aggregator. This is the term which you need to follow throughout the presentation, the data aggregator concept. Now, once the global trigger says that, okay, the window is open, capture the data, it sends it to the data aggregator. Here, it marks the data from which detector the data has come. There is multiple detectors in the left side. It will tell, okay, this detector was on at this time, this was on. It actually timestamp these two data packets, data and the trigger information. And then from here, it goes as a triggerless timestamp detector data to DAC processors. So this is a very, very simple view of the complex timing and trigger distribution of a Large Hadron Collider. Okay, I'm closing this section too. And before I go into the next section, I just want to revise what I have told in this section. Understanding the trigger concept in high energy physics. What is the advantage of trigger? Transition towards triggerless architecture. And the fourth one, formation of trigger type hierarchy based on latency. So in this part, I actually missed one point, is that if there are different detectors had got different latencies, and the important information for the electronics and computer scientist is that these signals are latency critical. It cannot vary with every time you reset or do power cycle or reset cycle or upgrade the firmware, this latency cannot vary. So these are all latency critical lines. Okay. Now I'm going to the third section. This is the LSC radio frequency swing with beam ramping. As I've told in the talk, that you will have to bear with me because I have to throw some jargons at you guys because it's a different domain. Let's break this term in a very step-by-step way, then you'll understand. LSC, as I've already mentioned, Large Hadron Collider. Radio frequency, you know from what range to what range radio frequency is. Then swing, which means there is something that makes the radio frequency swing. And then there is a beam ramping. And what is meant by beam ramping? Okay, let's go through the terms one by one. This collision of data points I'm hearing audio again. There's any questions or anything? Okay, I'm then continuing. LSC radio frequency. So during the collision, this is the beam dump. There is something called training beam. Just before the Large Hadron Collider start, there is a training beam is there, which actually trains the reactor and the collider before it starts actually capturing before it start the collision process and does the capturing of data. So here is the first part. It's the whatever beam it is circulating, it will dump it. Then the ramping of the clock beam is done. And there is an injection phase where a new beam is injected into the collider. And again, in this part, the ramping starts. And in this part, if you have remembered in the video, the particles are circulated multiple times to squeeze into something called bunch. And then from bunch, it prepare for the physics experiment. And then it is rotated across the LHC to collide at 4 experimental areas. Now, if you look at this beam graph, that is the current actually varies during this process, and the magnetic field. This current is actually the magnetic field current. And what happens actually, the radio frequency swings with this beam current. And there is a small table I have told you just to understand the picture, that how much time it takes for ramping down, that is 18 minutes, then plateau. So if you add this all together, you can understand it takes easily an hour and more just for configuration. So if there are some errors in Large Hadron Collider, it can easily go into shutdown of 1 hour or 2 hours. So when the beam taking comes, every physicist are very, very alert and on their toes to take the data. Now coming back to this topic, so I just mentioned you the radio frequency varies or swings with the beam ramping. Now the next part, that's the obvious question that is rising. What is the frequency that I'm talking about? The entire Large Hadron Collider works at 40 megahertz. Forget the fractional part for the timing, decimal part. It works at 40 megahertz, and the swing happens at 87 hertz, which is very negligible. It can cause PLL errors or those, but that's a topic for some other day, how this is handled. The important information is that this is called bunch clock. And the reason it is called bunch clock, because I have mentioned the particles are circulated inside the Large Hadron Collider. It is rotated at a very high speed that is called ultra relativistic speed. What this term means is that the particles are rotated in the Large Hadron Collider at 99.999% at the speed of light. That's why it is called ultra relativistic acceleration. And when these particles are bunched together and rotated, it is called bunches of particles. And the clock at which it is rotated is called bunch clock. And the frequency is 40 megahertz. And there is an orbit frequency which tells that, like you can take this example as a circulating bus. So this entire set of bunches rotate around 11 kilohertz or so. So this, I actually give you the concept of how the radio frequency swing happens with beam ramping. Now let's take you to the next concept of how to embed this clock in the communication channel. And before I go into embedding this clock in the communication channel, I want you to introduce to some of the fundamental terms that are in electronics but not used very commonly. And this is called the degrees of synchrony. I'm just reading the lines that are written in the PPT here. For a communication system to operate reliably, one of the 4 classes of the clocking methods are employed. Asynchronous, you all already know what is asynchronous, uses no clock signal scheme. Then there is a concept called synchronous, which uses same clock frequency, and you already know the phase of this, and this is called synchronous scheme. Both of these you know already. The third and fourth that is not used commonly is called mesochronous. It uses the same clock frequency, but you don't know the phase information. And plesiochronous, which uses the same clock frequency, but with drifting phase scheme. So in high energy physics experiments, we actually use all the 4 types of clocking methods. But in this talk today, I will only discuss the asynchronous system behaving as the synchronous. So in the next slide, I will just try to highlight in a very simple manner how an asynchronous system, which has got no clock inside, can behave as a synchronous system. Let's go. Yeah. So embedding clock signal in the asynchronous serial links. This orange colored block, that is the asynchronous serial link, as I mentioned in the last slide, it has got no clock inside. And it is capturing the data at the sampling speed of the clock. But there is a catch. In a typical asynchronous serial link, before I go into the fundamentals of the how clock is done, let me give you an example. What type of asynchronous serial links are there? For example, 10 GB Ethernet, it's an asynchronous link. Then PCI Express, it's an asynchronous serial link. These are all different types of asynchronous serial link that you use commonly nowadays. Even the USB, Universal Serial Bus, it's an asynchronous serial link. Now, what the physicists want to do, as I have mentioned in earlier slide, that the signals has to be latency critical, that the latency need to be achieved. Now, what the physicists want to do is to use the asynchronous serial link. The reason is that the electronics for the asynchronous serial link is pretty advanced, and yet achieve the benefits of synchronous serial link. So what they have done, they have replaced this elastic buffer with the inelastic buffer. Now, by what is elastic buffer? Elastic buffer is like FIFO, is the fast in, fast out. Then RAM, random access memory. Then there are dual port RAM. I'm not going into different types of buffer. So what this FIFO RAM this does is actually, these types of architecture are used when you are going for clock domain crossing. That is, you are, say for example, you are in 100 megahertz and you are crossing to another clock domain which is running at 101 megahertz. In that case, you use something called elastic buffer, FIFO or dual port RAM. But what the physicist found out, that instead of using elastic buffer and using a ratio of the transition of the rate, like for example, instead of going from 100 megahertz to 101 megahertz, why not go from 100 megahertz and jump to 200 megahertz, but make sure that the 100 megahertz data that is coming, it is coming at dual data rate. So that was the idea. And then the way to maintain the latency is to replace it by inelastic buffer. And that is a simple chain of cascader register. So when you do this two-step, that is, make sure the ratio of the clock frequencies are in proper ratio, and also if when using inelastic buffer, the asynchronous serial link behaves as a bounded synchronous serial link. And there are 5 major bullet points you have to remember when you design a design for high energy physics. First, it has to be frequency locked. For example, when you have a USB or a PCI Express, it actually locks with the clock that is in the PC. For example, in the USB, it will take the clock from the PC and it will run at that rate. So that's why it is called universal, because you can plug it in any system, in a Mac PC or any PC, and it can take the clock rate. But now anyway, because of Cypress chip, more of these things are standardized. But that was the idea of the original USB. And that is actually one of the requirement in physics. That is just the opposite requirement. The frequency has always to be locked. You cannot vary the frequency. And as I've mentioned already in the last slide, the frequency is 40 megahertz, in a multiple of 40 megahertz. And the next part is the fixed latency, because the latency is critical. Then the third is to make sure there is a very, very low jitter. Jitter is something which actually corrodes the timing information. I will not cover that part. In the question and answer session, you might ask these things, that whether you want to know these things. And then we got to timestamp the data point. And the last one, but not least, is the phase locked point. How to phase lock this design. For example, if there is a power reset or firmware upgrade or just a reset assertion, you have to make sure the signals are locked each time you do any of these cycles. So that's why these 5 constraints are very stringent in high energy physics. Now, in this slide, I have given you how the asynchronous serial link looks like and what it wants, without going into any deep technical details. Now, let's understand what is the term that is used in Large Hadron Collider for such a link. Like I've already mentioned, in commercial architecture, you have the asynchronous link like USB, PCI Express, 10 GB. In high energy physics, the term is called GBT, GBT is the term referred to as gigabyte transmission. And it has got a ecosystem. Like for example, when you plug an USB, it has got the male and female part. Similarly, when the PCI Express are plugged into, there are two slots, male slot, female slot, and there is a negotiation protocols. Similarly, in the GBT ecosystem, it has got the three very important part. One is the timing and trigger acquisition part. That is, data and timing are mixed in this block. This is a radiation hard electronics placed very close to the detector. And this is the GBT slow controller block, which takes the control information. And these two informations are integrated and pushed over the optical link using the protocol called, which is also termed as GBT protocol because of the GBT ecosystem. And then it is recovered on the receiving side using an FPGA, which has the GBT logic programmed in it. And it can uncover the packet that is formed in this side. So just remember, in the Large Hadron Collider, the asynchronous link that is used is termed as GBT. I'm not going into the details. You can, if you are interested, you can question me after the slide is completed. Typical representation tools used for signal integrity analysis. Now, when you develop this type of architecture like asynchronous signal serial link architecture, there is a dedicated branch in electronics called signal integrity analysis. And in this slide, I just want you to give you the glimpse of some of the representation tools that are used. One that you already know from your BTech studies, like the eye diagram. So the eye diagram actually gives you the opening of the eye diagram gives you the quality of the signal. The eye height will give you the any type of amplitude distortion, and eye width will give you any type of timing distortion. And this part of this graph where these two signals coincide, this give you the jitter information. And this part, if you zoom in, it will look like a Gaussian peak. And this is the jitter. The minimum the jitter, better it is for the experiment. And this graph shows that every time you reset a clock system, how much jitter it can have. So this is the representation tools that is used. And that is the corner part, right hand lower corner, this one. It shows the phase noise. Phase noise is something that you not use regularly. The phase noise plot is used when you want to know that for a particular frequency, say for example, 1 megahertz or 10 megahertz, what is the phase noise that is there? And since these are all clock lock signals, since these are all locked at a particular frequency, you are not that much bothered at the jitter or noise that is present at some other frequencies. So as we have already told you, the frequency of interest is 40 megahertz and the multiple of 40 megahertz. So since I know this already in experiment, I'm just giving you the figure, the 40 megahertz. Then the other two frequency that we monitor in Large Hadron Collider is the 120 megahertz, another is the 240 megahertz. And as you can see from this graph, when you use some kind of a jitter cleaner, say for example SI5344, that is the green color graph, the jitter goes a bit low. So every time when you go from one clock domain to another clock domain, one hardware to another hardware, there is a transition, jitter noise is added, and in between you need to put some kind of a jitter cleaner. And that is shown in this graph, that how a jitter cleaner drastically improves the signal quality. So this slide just give you the signal integrated analysis that are needed for this type of system to be built. Okay, in this section 3, I have covered 5 main points. What are the timing signals that are important in LHC? Types of synchronicities, then how to embed a clock in asynchronous serial links, a brief introduction to GBT's ecosystem, and the parameters to monitor like jitter, then inter-symbol interference. I haven't talked about that. You can skip that. And phase noise and latency. This latency is actually I was talking about when you do a reset. The latency or the skew in this case actually varies. When a skew varies in the signal, it actually affects the latency. So this is the plot that is used to measure that. Okay. Now I go into the last section of this talk, that is the section 4. As I mentioned earlier in section 3, the concept of data aggregator. Now, all of a sudden, why you in the high energy physics we are using data aggregator? This I have mentioned in section 2. If you can remember, the triggerless architecture. The data volume that is currently generated is in the order of 1 terabytes per second. And if you connect any processors, it will just going to, even if it's a grid computer, it will just going to get stalled. So that's why the concept called data aggregator has emerged in the high energy physics. And you can think of this concept as a router. I know nobody thinks about router nowadays, it's taken for granted, but router is a dedicated block in a network to handle the network load. Similarly, in high energy physics, because of the recent demands and a push for new technologies and future experimentation demands, it has gone for a data aggregation unit called data aggregator. The concept is data aggregation, different experiment call it by different name. So what it does, it actually captures the timing and trigger information from the high energy physics experiment. Then as I mentioned in the previous slide, that there is the asynchronous link in the high energy physics is called GBT. Here the data are captured at 4.8 Gbps. These are coming for multiple detectors that are there in the experiment. All these data are grouped together or aggregated in the data aggregation unit. And here I want to mention here why the term is called aggregation, not concentration or jipping. Why the term aggregation? The reason is that when you call data concentration, it means like you are concentrating the data for a particular time and then you are pushing to the next system. Similarly, when you are using the term called data routing, it means you are just routing to different data, but that is not the case here. It is specifically called data aggregation unit. The reason behind that, it not only aggregates from multiple links, like I have shown only 1 to 36, it is around to tens and thousands, 10,000s and more. And the timing for each are actually generated in this area. Proper timestamp and data put here, and it is processed real time and pushed into the next architecture of the computing architecture. So what actually this block does is actually takes the load of the computing architecture and also takes the load of the front-end electronics and separate it out as a separate model. And this helps in proper queuing of the data or channeling of the data. And here in this part, I am showing you the control signal. Since this is an electronics module, and as you can understand, electronics modules are very flexible and it doesn't hang like a computing devices. And this control system can directly assert control signal here. Say, for example, stop the data acquisition immediately because DAC has gone down, or maybe the trigger or data detector has gone down, or maybe there is a beam dumping that is happening. This control signal directly assert here, and you can directly take down the data flow. What this means for the DAC, that the system is not jammed, and whatever data that has been captured or the bad data that has processed, we can successfully drop those data. So this is a new concept introduced by the high energy physics experiment groups. In the next slide, I want to show you how this concept of data aggregation are used by different experiments, and they are using different name for the same thing. I'm just reading the line here. the new readout architecture in upgrade or future high energy physics experiment use data aggregation unit, but they are called by different name. In Alice experiment at CERN, this is called that common readout unit, which uses the FPGA of ARIA-10 FPGA. It's an Intel FPGA. Then for the Atlas experiment at CERN, it is termed as Felix, which is an FPGA PCI card. It's still under not fixed what type of card they are going to use. At the CBM, it is called DPB Data Processing Board, which uses Kintex 7 FPGA. At the LHCB, that's another detector at CERN like Alice. It's Sol 40, Odin 40, Trigger 40, Tail 40. These are all referring to the same data aggregation unit that are dedicated for different functionalities. And it uses the same architecture as ARIA-10, and actually it uses the same hardware. Just the names are different because of its functionalities. And the fifth one is the ITER. ITER is the Kodak. ITER is a fusion reactor that is coming up in the south of France. If this experiment goes well, then we're going to have a clean energy in future. So it's a control fusion reactor, Kodak. It's using, and this using something called distributed network, which I haven't covered in this topic. Now, here I am just going to give you the complexity of the data aggregation unit. In the previous 2 slides, I have just simply portrayed how the data aggregation unit looks and what type of functionality it can do, and how it is termed in different names in different experiment. So in Alice experiment, it is referred as common readout unit. Here I am showing in Alice experiment how the common readout unit takes the data. So these are the front-end detectors which are situating close to the Large Hadron Collider collision, that is the particle collision that are happening. Here it is like the front-end trigger unit, FOSS unit, time of flight, zero detector collinator. All these are sending some complex information, trigger input to the central trigger processor. It does some basic AND or XOR logic, basic Boolean algebra here, and it processes the information and send it using the local trigger unit. Here there is a trigger distribution chain. From here it goes on to the front-end electronics. These are the critical window. Remember in the previous slide I have told you, it asks that open the window for the front-end detectors. Here the detector are asked that there is a data collision going in, start acquiring the data. And this detector starts acquiring the data. And then there is an other trigger which acts as a timestamp for the common readout unit. This is like, for example, if you got the Higgs boson particle, you don't know yet that if there is a Higgs detector or not. You just give the timestamp, and since it is happening at the picosecond level and it is not possible to process it real time, it just put the timing information with the raw data. As a triggerless data, this information is pushed into the data acquisition chain. Here it is called as online-offline facility. Here the data, that is the DAC processor, spreads the data across the world in an offline manner. The people in different experiment search whether a Higgs boson particle, a particle like Higgs boson is detected, because you need to understand this is an experiment, not a production chain. So in experiment, you always don't know the signature of the particles. Right now, the physics people know the signature of the Higgs boson particle. Maybe in this year or next year, you don't know that a new particle is discovered, and people doesn't know the signature yet. For that type of thing, this trigger time informations are very important. And since we already know we are going into the technical boundaries, that's why the triggerless is given, since in Higgs boson already is in picosecond level. Maybe the next discovery that will be done even below picosecond. So that's why the LSC is already prepared for that. And this is the common readout unit, the data aggregation unit that the LS use, and it has got PCI Express link, and which actually this block is called fast level processor, and then from here it goes into the network, and this goes to different or worldwide networks. In the next slide, I want to just give you the glimpse of how this board looks. It's a very compact electronics board. Not going into the technical details here because of time limitation, but surely you can see that this is a raw board before the heat sink or all those stuffs are put into it. That's why you can see the card at this level. So this is called the common readout unit, as I mentioned in the previous slide. That acts as a data aggregator unit. And here the GBT links comes in. GBT links comes from here. These are called SFP plus, quad SFP plus modules or mini pod. These are commonly called in optical technology as mini pod. And here is the FPGA that is sitting. This is the Intel Arria10 FPGA. And so the GBT links are coming here. After it is an optical link here, from here it gets converted into electrical one, goes into one of the mini pod, spread throughout the board and goes into the FPGA, and the processing is done here, and it is again thrown out using the PCI Express link that is in here. What this board capable of is actually each of these mini ports supports 12 GBT links. So you can understand 1, 2, 3, 4, that is 8 blocks are there. 96 GBT links can be captured simultaneously here, processed and pushed to the PCI Express after doing data processing. Now the advantage of using FPGA, that those who are new here don't know that the advantage of using such a FPGA-based architecture in high-energy physics is because of the reconfigurability, parallelism, pipelining. It allows you to rapidly prototype the system and dynamic configuration, and also reduce time to market. So this board that has been built for high-energy physics can also be marketed for other future experiments like the commercial one. Maybe someday you can see this sitting in your lab, because this once it gets commercialized, now it is at the experimental level, it's quite costly, but once it gets commercialized, it will be like a normal block which is doing some signal processing stuffs, and you are playing with it. So I'm closing this last section here. So the key takeaway of this section 4 is the data aggregator in high-energy physics. How the concept of data aggregator is used in high-energy physics, example in CRU. Application of data aggregator in different high-energy physics. And the need for synchronous, parallelized, pipeline, and reconfigurable architecture, which is called FPGA. And I forgot to mention the full form of FPGA, field programmable gate array. And remember, the word field is used here not because of magnetic field, because it is in actual field. That's why it is called field programmable gate array. Okay, and that's all. So I can close it. Thank you.